So the motivation for this talk was to answer the question, what's the relative performance of these three interfaces? And it started as a question from a customer. And intuitively, I think a lot of people that have been around Postgres for a long time sort of know the answer to that, but I wanted to be able to give a quantitative answer. So I set out to come up with a test methodology that was reasonable, that could answer that question in a number of different scenarios. So specifically, I wanted to look at connection time for the interfaces, the actual query result retrieval. What's the difference if you use alternate retrieval methods? And what I'm talking about there is copy interface versus the standard interface for libpq and for JDBC. And actually, libpq has an additional interface that went in just a few years ago. It's a one row at a time interface that's different than the standard result set, pull the whole thing back interface. So I wanted to test that to see how it performed as well. And I wanted to test the difference between materializing to a file versus just holding the data in memory. So that covers a number of different scenarios. In some scenarios, you're bulk moving data and you want to write it out to a file for some reason, some kind of ETL or some kind of quality assurance type data comparison, and in some cases you want to just see how is your application going to perform pulling data from the database and using it. And secondarily, I also wanted to be able to get data on things like what's the difference in time between if you connect every time versus connect once and run a bunch of queries. And again, it's going to be fairly intuitive to everyone that it's better to connect once, but when you're talking to clients and you tell them this, they're like, yeah, okay, but how big is the difference? And that's one of the things I'm going to be able to show you. As well as what's the difference between doing set operations versus single row operations. Same thing, intuitively sets are going to be better, but how much better? Does it really make that big of a difference? And then also, what's the difference in timing versus local versus remote? If I've got my application on the same machine as my database, or if I have my application on a different machine, how much impact does that have? So the approach I took was I created being a Postgres guy, I'm going to do this testing using Postgres, right? So you'll see that pretty quickly, that it's very Postgres focused. Hopefully, some of the ideas here might even inspire you to do something similar. I'm going to create a C database, and then I've written a bunch of command line clients that are actually going to do the connecting and the querying. I'm going to vary the conditions for those clients. I'm going to collect a duration each time it runs, and then I'm going to analyze the results. The major components that are involved here are the command line clients themselves, so they're written either in C or in Java. There's a Postgres extension that I wrote in order to facilitate this. This is kind of an interesting, don't try this at home sort of extension. All it does is it executes whatever command you give to it out at using a system command and times the result. So it made it really easy from within SQL statement to run a command and get a pretty good accurate time for that command without going crazy trying to figure out all the quoting and shell expansion and all that kind of stuff. And then there's a driver function that kind of facilitates this whole thing, and there's a bash script that launches it. So in terms of flow, the launcher script is going to connect to the database basically using pSQL. It executes the function, the PLPG-SQL function, which is then going to call the extension, which is going to execute the client, and then the client is going to finish, and then the extension is going to report back the time, and all of that's going to go back into a table into the database. So the whole thing, once you launch it, is automated. It actually runs for about 18 hours, so it's a good thing it's automated. The individual command line clients, I wanted to make them native for the interface that I was testing. So libpq and ODBC are both C, written in C. And the JDBC client is written in Java. Now, full disclosure, I am no Java programmer. I did get some advice from Dave Kramer, who's the JDBC author, about how to do things in a reasonable way. And as I mentioned earlier, I'm not going to be able to show you the source code today, but I set out specifically to write these programs so that they were structured pretty much as identically as I could make them, given the fact that 2 of them are in C and 1 of them is in Java, and they have different interfaces. So the Java program is actually written, Dave even said this, he said it looks like a C program wrote this Java, and it does. So there's probably room for improvement on the Java side if someone who is really a Java program got in there, but we can talk a little bit about that later on. Each one of these is going to be called with an identical set of command line arguments, and they're designed to handle all of these variety of conditions that I was talking about. The C extension is just a simple way to execute the commands. It gave me complete control over the escaping. It makes it easy to time the duration and actually to collect that duration. So driver tables were the tables that I'm using to set up the various test conditions. There's a table called interfaces, and that right now just has libpq, ODBC, and JDBC. One of the reasons I did it this way is because in the future, we could test other interfaces, right? There's actually a JDBC next generation driver out there somewhere that Dave asked me to test at some point. I had thoughts of maybe there's a native Python interface that doesn't use libpq that I thought about testing. And there's probably some other things that we might eventually want to test. This alternate client copy table is what's handling which interface we're going to test for the driver. So the ACC, and I've used shorthand through a lot of this because there's so many different conditions, it would get really verbose on the slides and hard to keep track of. And so I've got a lot of shorthand in here. ACCN means alternate client copy, normal interface. ACCA means the alternate interface, which really only applies right now to libpq, where that specifically designates the 1 row at a time interface. And then ACCY is the copy interface, which applies to libpq and JDBC. There really was no direct copy interface in ODBC. The conInfos table is giving me my connection information, so that's where I'm going to control. LCL IPC means local interprocess communication, so that's your BSD sockets connection. Local TCP would be a local TCP connection, and RMT, remote TCP, is obviously a remote TCP connection. So for instance, Java cannot have a local IPC connection, but libpq and ODBC can, so that limits the sets to some degree that JDBC can participate in. This print fract dest is how many of the rows I'm going to print out and where they're going to. When I originally set out to do this, there was some thought in my mind that I might do like fractions of it being printed to file instead of all or nothing. In the end, I ended up deciding it was best just to do all or nothing. So basically, you can have print none, which is everything's just kept in variables in memory. You can have print all null, which means I'm going to print it to standard out, but I'm going to send it to dev null. And then print all file means I'm literally going to print it to a file on disk. One of the things I should say also, just so I don't forget later on, eventually I'd like to open source this whole thing. It was kind of developed under a contract. I've gotten permission to open source it. And I just really need to get around to cleaning it up a bit and doing that, figuring out which license it's got to go out under and a couple of things like that. But if you were to try this in its current incarnation yourself at some point in hopefully the near future, be aware that these files that it creates, some of them are fairly large and there's a lot of them, and so it eats up like 100 gigs of disk space when you run it. And then this SQL strat iter table is kind of my strategy for how many rows am I going to bring back and how am I going to bring them back. So SQL 001 means I'm bringing 1 row. The 0 means I'm going to connect every time. and the 50K means I'm going to run it 50,000 times. As opposed to SQL 50K, which means I'm going to grab 50,000 rows per query. I'm going to connect every time, and obviously if I'm doing a 50,000 rows all in one query, then whether you connect every time or not really doesn't matter. But I'm only going to do it once. So I'm getting a direct comparison between what does it take to pull 50,000 rows one at a time versus 50,000 rows in a set. And I'm going to do that both with connect every time or connect once. And then this third case is 10 million rows. So this was to get an idea of what it would look like if you were doing kind of more of an e-tail kind of load. So that it's going to grab 10 million rows in one query in both cases. So I had this conversation with Stephen the other day. He was telling me that Cartesian joins have no use whatsoever.
I didn't say that.
So here's an example where I actually have a use for a Cartesian join, because I don't have, as I was going through just a minute ago, some of these cases are linked to a specific type of interface. So they're not available to all interfaces. In those cases, I need to do joins. But in the cases like the where and how many am I going to print, and how many rows am I going to query, and how am I going to get them, those applied to all the cases. So in that case, I'm just going to do a cross join with those two tables so that this thing basically explodes out and gives me all my test cases. So this is an example of what a test case looks like. The test case string is just sort of a concatenated short description that I was going through. So ODBC, LCL, IPC is the ODBC interface, local, BSD socket, SQL 001 is one row at a time. 0 means I'm going to query it every time. 50K means I'm going to do it 50,000 times. ACCN is the normal interface. P-all means I'm going to print them all, and null means it's going to go to dev null for that particular case. And then what you can see below it, and hopefully you can see that in the back. I know it's kind of small. I didn't expect to be in this big of a room. But what you see below it is the actual command line syntax that's going to be used to run the test client. So ODBC test is the name of the client, and I've got the same set of options basically for each of the clients. So I can say C is my connection parameter, and with ODBC that's a data source name. Obviously I have to set up those data sources in advance as well. The S is the SQL I'm going to run. P is whether I'm printing. N is how many times I'm going to run it, and then I redirect it out to dev null, and standard error goes to dev null as well. So that's how this whole thing gets controlled. The 50,000 row table is basically 10 columns, generated like this using generate series. Each of the, or at least 9 of the columns are 99 characters wide, just to give it some row width for the test. And it's indexed on ID. The 10 million row table is similar, except I made some of the rows less wide so that the whole thing would be a little bit smaller. Again, when I first went through this, I did a much larger 10 million row table, and I ended up using 300 or 400 gigabytes of disk space the first time I ran this thing. I decided that was just a little bit too much to deal with. The test results table is where I'm going to aggregate the results from each test. What this is going to look like is I get the full test case so I can resolve into, what parameters were used for this particular run. I keep an iteration number, and that's because the driver function that I'm using allows you to specify how many times to run each case. And my wrapper shell script, I decided to default it to 3 so that it wouldn't just run each case once. I wanted to get some averaging out of this. So this keeps track of which iteration within the run, and the timestamp is really, I'm using now for that. So that timestamp is going to be the same for every test case that was in a given run. So I could theoretically say this run of the tests or all have the same timestamp. Could probably redo this and add some kind of a serialization instead so that you're not trying to match up on a timestamp. But so far I haven't actually needed that level when I've gone through the analysis on it, so it doesn't really matter too much. And then of course the duration, which was collected by the extension function. In order to do some analysis on it, I needed to explode the test cases back out. So this view just basically splits out the various aspects of the test case back into individual columns for me so that I can run some analytics and slice and dice things in different ways. The driver function itself, exec test cases, it takes a couple of paths. And that was so I could deal with things like, making sure I'm looking at the correct libpq, because I tend to run on machines that have 4 or 5 different versions of Postgres on them, and I wanted to be sure that I was actually using the version of libpq that I wanted to use. I needed to have the class path set for Java, so I pass all of that stuff into the function, and then it executes the client using the correct paths. And then again, as I mentioned, I set how many times I want to execute each of the test cases. It returns which iteration I'm on, the actual identifier for the test case, and the duration. And I think right now there's something like 268 total test cases, and if I iterate 3 times, it ends up being like 864 tests that get run for a given execution of this test. So that's, like I said, that's why it ends up taking, I think, somewhere between 12 and 18 hours to run. So the launcher script kicks off the entire automated test. It sets the variables and calls exec test cases using pSQL. So it's pretty simple. Really just uses pSQL to launch this whole thing. And as I said, 288 test cases per run times 3. Okay, so this is the part where I was going to drill into the source code for you. I'm not really able to do that, unfortunately. What I can say about it is, as I said earlier, they're all structured the same, the clients. I used getopt to handle the options because that was convenient. Getopt is GPL, so if I open source this thing, it'll have to be GPL unless I decide to rip out getopt and replace it with something else. There was an equivalent to getopt there was a Java library that was actually almost identical to getopt that made it really nice. I think that had actually a more liberal license than GPL. So in any case, I need to take a look at that before I open source it. How many people here are familiar with C programming with libpq anyway? So there's a small number of you anyway, or about 30 of you maybe. So I mean, this is pretty standard stuff. Some of the code was swiped right out of DB-Link in the contrib code. Without showing it to you, it's going to be, I guess, kind of hard to explain. It's fairly complete, self-contained. It's got full help built into it. It takes all the different. I didn't bother with long options, but that's something that could be added. Or actually, I do have long options. I just have never used them. For ODBC, you do need to set up ODBC instant ODBC INI. That's fairly straightforward, even on a Linux system. Probably the main thing to understand here is that in order to do the test, I wanted to have a separate data source name for each type of connection I wanted to use with ODBC. So there I had one data source name, which was basically using BSD socket on the local machine, one data source name that was using TCP on the local machine, and one that was doing a remote connection to another machine. And if you're not familiar with how to do BSD socket with ODBC, you basically, where you would put a host, you'd put /temp or wherever your sockets directory is, and Postgres just knows to use a BSD socket connection. The Java code looked a lot like the C code, to the horror, I'm sure, of any Java programmer that looks at it. One of the things I struggled with was how to deal with the bulk copy data coming back, and again, not being very familiar with Java, a couple of iterations of trying with that, I had the thing blowing out memory and all sorts of other ugliness. I finally talked to Dave Kramer, and he gave me a little class that would allocate memory in big chunks and sort of grow as you needed it to grow, and I ended up using that. And after doing that, the results for Java looked a lot more in line with what you might expect. How many people here have written C extensions for Postgres? Probably the same group. Oh, even less. So it's unfortunate I can't show that. It's fairly boilerplate. If you look at any of the source code in the contrib directory in the Postgres source tree, there's loads of examples. But this one is a very simple example of an extension. It takes the argument basically as a text string and sends it out to the system with a pipe, pulls back the result that the program sends back to standard out, and just times it on either side of the start and the finish and returns the time. And if you're not familiar with it, when you create an extension in recent releases, thanks to Dimitri, largely, you can do create extension module name, and it just gets installed. It's much cleaner than it used to be years ago. The sequel for doing all this, again, I've kind of gone through some of the details already when I described the tables. There's a few more bits to it. I've created some views. Actually, I've got some of the view code on the slides later on, so you will get to see some of that I used for the actual analytics. Mostly, it's just creating those little tables, putting the seed data in them that's needed by the tests, creating the function that runs the driver, and creating the view on top of the test cases. And as I said, the run test.sh is just a very short bash script that really just shells out to pSQL and runs the thing. The interface variations, ODBC, libbq, JDBC. This is in this ConInfos table. Now that it's expanded out, you can see a little better that what I've actually done here is this ConInfo is in the form of the argument that I'll give to the client. So literally -c, DSN, PGSQL IPC is the command argument that'll be used for this test case, local IPC for ODBC. Halfway? Okay. The other kind of interesting thing here that I didn't even realize until I started doing this, but a couple of releases ago, someone added the capability to use URIs as ConInfos for libbq, which is pretty cool. So now this thing can actually look a lot like the JDBC URI. It's not exactly the same, but it's pretty similar. This is the table that's handling the strategy and the number of iterations. So in here, this is the description, SQL 0001 means I'm going to select one row at a time. I'm going to connect every time, and I'm going to do it 50,000 times. And so this is the command line option for the SQL itself. You can see what I did was I just have a select star from the table where the ID is some fixed value. And since there's a primary key index on that column, that's going to be a fairly fast index lookup. And I think it's also, at least somewhat of a common use case. The strategy is just K0 means how many times am I going to connect, and the number of iterations is -n, and the number of iterations. For the print frac test, again, the description goes in the first column here. -P1 means that I'm actually going to print out all the results, and destination just has the results. So basically, the way it's defaulting, the stuff that gets printed to files all go into /temp to a file with a base name of if test out, but then it gets the case appended to it, so you get one file basically per case that actually gets printed. And that turns out to be useful, so you can go look in those files and make sure you actually got the results that you expected to get. And the alternate client copy, ODBC just has the one row. libpq, you can see, has 3 rows, so it's got the -A and the -Y, which are just basically Boolean options that are saying turn this option on or not. JDBC just has the 2. The -Y is for the copy, and the A is for the one row at a time interface. Okay, so this is this is probably a bit hard for people in the audience to absorb, but I'll try and describe it for you. What I'm doing here is a window aggregate, and within a group, and I'm selecting my group as basically, in this particular case, I'm grouping on the type of SQL statement, the number of iterations, location, the type of communication, strategy, and the print, whether or not I'm printing. And so within that group, I end up with a number of rows, and within those number of rows, I'm going to pick out what is the difference between the current row and the minimum value in that group, and I'm going to do the same thing for basically the range. And the reason I'm doing that is because with all of these different kind of connection and all these different strategies that I'm doing, you end up with several groupings of times that are orders of magnitude different. And if you want to be able to do the analysis across these very divergent groups, you have to standardize the data somehow. So one way to standardize is you subtract the average from everything, and then you divide it by the standard deviation, and that's called normalizing the data. But that really only applies if you have data that fits a bell curve, and I wasn't confident that this really fit a bell curve. So this is a different form of standardization, but it basically takes all your data and it fits it in a range from 0 to 1. So now that all of these different groups are fit into a range of 0 to 1, I can kind of meaningfully combine them and look at the differences between the groups. Now, in some of the slides, I'm also going to show you raw data too. So in case you don't believe that this method works, is worth a darn, then you can actually see some raw data. So in this first one, I'm using that view that I just talked about, and I'm giving you the overall results of, in this case, I'm combining the libpq and the type of interface. So these are really what I consider to be the interfaces, right? So libpq with the copy, or libpq with the one row at a time, or with the normal interface. Each of those I'm calling basically a candidate interface. And you can see I've kept track of the group size. So I ran this set of tests that are in here 3 times. So 3 times 3, there's 9 rows basically representing each test case. And you can see that the libpq with the alternate one row at a time interface actually beats out the normal interface, which is maybe not surprising to some people. And there are definitely some cases where the alternate interface is not faster. But overall, across all these test cases, sort of averaged out, that one is by far the fastest. And I thought I had sorted these, but apparently oh yeah, I guess I did. Just not reading it right. So the normal interface for libpq actually came in second, and the copy interface came in third for libpq. So libpq, hands down, if you take all of this stuff as an aggregate, is the fastest interface. The copy interface for JDBC actually performs pretty well. And you also see that somewhat in the raw results. The standard interface for JDBC actually was the slowest across, again, all of these tests. And ODBC came in here at 5th. So this is another one of those window functions. I'm just basically grouping over a different type of data in this case. And these slides will all be available online, and at least once I get to open source the code, you can try this for yourselves. But you can study at least and try and understand what I did here, hopefully offline. So here what I'm doing is I'm looking at what's the difference between whether I'm doing a local BSD socket connection, whether I'm doing a local TCP connection or a remote TCP connection. So again, this is aggregated across all the different test cases, all the different possibilities using the standardized data. And of course you can, as you would suspect, the BSD socket locally is the fastest by a large margin. But the local TCP is, if you use this as sort of a percentage, you can say it's about 10% slower. So it's not significantly slower, whereas going remote has a fairly significant cost to it compared to the other two. And again, in the raw results, we'll see some more on that. This third one, I'm just trying to show you the results of a number of cases sort of all together so you can do the analysis in your head as you're looking at it. It's two different machines that are connected on the same subnet, and they're both literally plugged into the same switch. Huh? They're both plugged into a gigabit switch that's, it's two machines sitting next to each other on a desk, basically plugged into the same switch. So it's about as, it's not a high-end switch, but it's probably about as good as you can get unless you want to do a direct cross-connect or something. I'm not sure. I don't think we were limited on bandwidth by this. This is.
I think it costs for 2. It was lower weight.
Oh. Okay.
Yeah.
So maybe we'll try it again with a 10 gig switch at some point. So the idea here was to look at what is the impact of a couple different things. What's the impact of doing the query on the 50,000 rows? So here I'm doing the 50,000 row query. Whether you're doing connect every time or not doesn't really make any difference, and you can see that is borne out in the data. You look at these numbers, this timing is about 0.3 seconds. If you come down to this bottom one, so all of these cases are querying essentially 50,000 rows. It's just using different methods to get 50,000 rows. So at the very top here, 0.3 seconds is when I'm doing local BSD socket connection, and I'm grabbing all the rows at once. Versus the bottom of the heap here is going on 400 seconds. And that's when I'm doing one row at a time for 50,000 times across the remote connection using TCP, and I'm connecting every time. So if you want to have some idea of the cost of doing some of these things the wrong way, this is it. 400 seconds versus 0.3 seconds. And I couldn't tell you how many times I've run into clients that complain about something being slow and they're using an ORM and they've got their app on a different machine. And when you start looking at what they're doing, their ORM is doing effectively this. Now I know there are ways to tune the ORM to do the right thing, but a lot of people don't even pay attention to that, right? They're developing their app, it's toy data when they're first developing, everything works fine, and then they roll it out somewhere and the first time there's significant data on it, it gets slow, and they want to know why. And this is what you see a lot. Even if you're connecting every time using a local TCP connection and running 50,000 queries, it's still 200 seconds, but you notice the difference there between local and remote. This is, again, just across this little switch. The time is doubled. So, as I said, although a lot of the information here is sort of intuitive, and I think probably a lot of people already know that, at least in a qualitative way that, yeah, this is going to be faster than that, this makes it kind of a hard reality, and you can show it to people and say, look, don't do this. All right, so now I'm going to get down into some more detailed data. This one is one row at a time, 50,000 times, using the BSD socket, connecting every time. So in this specific case, you can look at the difference between the interfaces that we tested. So this is basically down to the raw data. And in this case, the standard libpq just slightly did better than the alternate one row at a time interface. The copy interface, though, surprisingly, querying one row at a time using the copy interface, which I don't know why you would ever do that, but it's really not a whole lot slower. You know, it's 167, 168, 169. So the difference in timing is not that great. Copy in libpq is actually pretty efficient. And ODBC is the worst, and it comes in kind of a significant difference at 240 seconds, so a good bit slower. Now this is one where we're doing the one row at a time, 50,000 times using local sockets, but we're only going to connect once. And we're printing it out to a file. And so now the timing is way down. The best timing here is not quite 8 seconds. And you have very similar results. The libpq normal interface is at 7.7. The alternate interface is at 8.3, and the copy interface is at 8.4 seconds. The ODBC comes in about double, 16 seconds. So now we're going to switch and we're going to do TCP and connecting every time. So we're back up to the, now in this case we're at 200, almost 200 seconds. libpq, again, normal interface wins at 184 seconds. The alternate interface, 185 seconds. The copy interface, 187 seconds. Now here's the first time where, since we're using TCP, we've got JDBC in here. And JDBC copy interface is a little bit slower than libpq, but not terribly so. It's right at 200 seconds. And the standard JDBC interface comes in at 206 seconds. ODBC is, again, far behind at 256 seconds for this case. Same scenario basically, except we're just going to query once. We're back down into the tens of seconds range. The order has switched a little bit on libpq. So libpq alternate interface actually just slightly nudges out the normal interface in this case. The copy interface is still pretty much right in there. It's 11.6 to 12.6. JDBC copy interface, again, does fairly well at 15 seconds. The normal interface for JDBC comes in at 20 seconds, so almost twice what libpq is doing. And ODBC is at a little over 22 seconds. And remember, this data is based on 9 runs of each of these test cases, so it's not just a single run. This is with not only averaging, but averaging over 3 separate periods of time. And I can also tell you that as I was going through this, I was kind of updating the slides after each run, and the numbers didn't really change as I was getting more averaging, and they barely changed at all. So there's a good bit of consistency to the data as well, at least for my hardware. So now if we're talking a remote connection, connecting every time, this is kind of the worst case scenario. libpq normal interface wins at 380 seconds. The alternate interface at 381 seconds. And the copy interface here is just a bit slower this time at 398 seconds. But again, libpq tops out the chart. JDBC is coming in at 430 seconds for the copy interface, 437 seconds, so about 10% slower. The normal JDBC interface is pretty close in this case, 443 seconds. And the ODBC is really kind of horrible in this case, 529 seconds. Change, yeah, okay. This is a remote host, one row 50,000 times, but only connect once. libpq, again, it's 26 seconds for the normal and the alternate interface. The copy interface is at 44. Copy interface for JDBC is actually 41. Copy interface for JDBC is at 44. I've not tried to use Wireshark or something like that, if that's what you mean.
That might be interesting to see if there's any significant difference in what they're really doing under the over to justify the difference. Java's just slow, man.
Hey, one of the reasons I wanted to give this talk is because I'd like to get other people involved. And like I said, part of that's going to depend on me being able to open source it, which at this point I've got permission. So if you wanted to have the code, I can give you access to the code and you can start looking at it. I'd like to get other people involved in doing this kind of testing. And I also think that potentially this could become sort of an infrastructure for doing performance testing in general. But so I think he was next. Yes, so again, this is, on my very last slide where I talk about things that we might do in the future, this is some of it. So what's the next question? Huh?
Can you summarize that question for the benefit of the
Well, it was more of a statement than a question. He's talking about the fact that you can control with JDBC whether it does prepared statements or not, and there's differences in the way JDBC works compared to libpq, and that may explain some of this difference. For my purposes, I was just trying to see what the difference was. Okay. I've got like 5 minutes left, so I'm gonna try and see if I can get through the rest of the slides. And we can a lot of this is the same information again. Query once, 50,000 times. Again, JDBC well, that's where I just was because I had backed up. All right, so this is across the remote, querying 50,000 rows once. libpq down in the half-second range. JDBC copy interface is about 2/3 of a second. ODBC is just under a second, and then JDBC is at 3 seconds. So again, it may be what you're saying is being seen there. 10 million rows. So this is 10 million rows, whether you connect once or not, it doesn't matter because I'm only running the query once. libpq alternate interface, one row at a time, actually beats the copy interface in this case, which I found very surprising.
Why do you think that is?
I've not tried to speculate at this point why. I just noted as an interesting result. And like I said, there's a lot of averaging going on here, so it's I'm sure, at least given my test setup and my clients, it's real. I haven't really tried to drill in and figure out what's causing it. But that row at a time interface doesn't really have to allocate a lot of memory, so maybe it's because of that it's winning. JDBC copy interface actually does right on a par with the libpq copy interface for this large number of rows. The normal interface is not very far behind. ODBC and normal JDBC are way behind, and the normal JDBC in this case is really horrible. So, again, not every company that's using Java maybe as enlightened as you are in terms of how to use it well. And that's part of the lesson here. Because we get lots of questions as database people, how to make my database run faster when that's not where the problem really lies.
Yeah, it's just natively, just if you write it out of the box, you don't do anything special, Java's going to use 2 to 3 times the RAM that the equivalent C app would use for the same data structures.
So this is localhost, more or less the same results. In this case, I was looking at 50,000 rows printing to a file. I was just trying to show the difference between, I'm not even sure what I was trying to show the difference between. These are all just the normal method. So it's comparison of the normal without considering copy and not considering the one row at a time interface, just to get them all on one list. So you can see it goes from 0.2 up to 3 seconds. So in terms of future work, pretty much the end of the talk. There's obviously a lot of things that could be done to expand on this. I've only had limited amount of time to put toward it, but I would like to see it expanded on different versions of the JDBC library, different tuning for JDBC, doing a server-side copy and then transferring the file and comparing that to doing bulk copies from the client side, trying the .NET provider, the Python provider, prepared statements on libpq versus, because JDBC is using prepared statements. SSL connection, that's something I completely avoided here. And that, I'm sure, has a large impact. Maybe not so much if you're only connecting once, though. So in any case, I think I'm right out of time, so thank you very much.